Right now, as you're watching this video, quantum theory suggests that at the smallest scale, reality may exist as a cloud of possibilities. But when a measurement is made, one definite outcome appears. Why? Nobody knows for certain. For nearly a century, physicists have watched this happen in laboratories every single day. The equations predict it perfectly. The experiments confirm it. But the mechanism behind it remains one of the deepest mysteries in modern physics. If reality exists as possibilities, as a cloud of probabilities waiting to become real, then what turns those possibilities into one definite outcome? In the last episode, we asked a question that changed everything. Does reality exist before we observe it? We discovered something unsettling. In the quantum world, the answer appears to be no. Before measurement, a particle doesn't have a definite property. It exists as a wave function, a mathematical description of all possible outcomes, spread out in space, in time, and probability. But the moment we measure it, something happens, the wave function collapses, all those possibilities vanish, one single answer appears. The question that's been tormenting physicists for almost a century is simple and profound. What actually causes that collapse? Let me start with what a wave function really is, because this is where the mystery actually begins. Imagine you throw a stone into a still pond. Ripples spread out in all directions. Where the ripples are strongest, the water moves up and down the most. Where they're weak, barely a tremor. The wave spreads across the entire pond at once, but it has different strengths in different places. A wave function works almost the same way. It describes a quantum particle as a wave spreading through space, except this isn't a wave of water, it's a wave of probability. At any given location, the wave function tells you how likely you are to find the particle there. Where the wave is tall, the probability is high. Where it's flat, the probability is low, but the wave extends everywhere. The particle could show up anywhere. That's the state before measurement. The particle is in superposition. It's like being in all possible places at once, weighted by probability. This isn't philosophy. This is what the mathematics of quantum mechanics literally describe. Now here's where it gets strained. The moment you measure the particle's position, the wave function collapses. Instantly, the entire wave vanishes. All those probabilities disappear. You get one single location, one answer. The particle is here, not there, not everywhere. The wave function goes from being spread out everywhere to being concentrated in one point. That's the collapse, and nobody actually knows why it happens. This is the real mystery of quantum mechanics. Not superposition, not entanglement, not even the measurement problem itself. And the mystery is what causes the wave function to collapse. Here's what we know for certain. When you measure a quantum particle, you get a definite answer. If you measure again, you get the same answer. The particle is now in a definite state. The wave function stays collapsed. It doesn't spread back out until you measure it again in a different way. Then it might collapse into a different answer. The transition from possibilities to certainty is real. It's measurable. It happens every single time without fail. But the mechanism, that's where physicists start disagreeing wildly. And the most common explanation is called the Copenhagen Interpretation. It's been around since the 1920s, and here's what it says. Stop asking why the collapse happened. Just accept that it does. The wave function isn't something physical. It's not a real thing vibrating in space. It's just a mathematical tool, a tool for predicting the outcome of measurement. When you measure, the tool does its job. It predicts an outcome, and reality matches the prediction. That's the whole story. There's no deep mechanism, no hidden process. The collapse isn't something that needs explaining. It's just what the universe does when we measure it. Some physicists find this deeply unsatisfying. It feels like the physics is giving up. Like we're saying, the universe works this way, and you're not allowed to ask why. But here's the thing. Copenhagen works perfectly. We can build quantum computers with it, and we can predict experimental outcomes with stunning precision. The interpretation that refuses to explain the collapse is the one that makes the most accurate prediction. Maybe that's telling us something. But wait, what if the collapse isn't what we think it is at all? What if it's not a sudden snap, but a gradual fade? What if the answer has been happening around us the entire time and we just haven't noticed? Then there's an explanation that's gaining traction in recent years. It's called quantum decoherence. And it says the collapse isn't an instantaneous magical event. The wave function doesn't really snap into one state. Instead, it gradually spreads and spreads until the environment interacts with it so much that the superposition becomes physically impossible to recover. Think of it this way. Imagine a soap bubble floating in the air. It's delicate, one touch and it pops. But if you leave it alone, it still might pop because air molecules are constantly bouncing into it. The bubble doesn't last because the environment keeps interfering with it. A wave function in the real world is similar. It's constantly being bombarded by air molecules, photons, radiation, thermal energy. These interactions measure the particle over and over. Each measurement causes tiny collapses. Each collapse refocuses the wave function. Eventually, after countless interactions with the environment, the wave function becomes so concentrated that it's effectively collapsed. It looks like a single outcome. All other possibilities have been measured away. This explains why we don't see superposition at large scales. A cat is made of trillions of atoms. Each atom is being measured by the environment constantly. The environment collapses the cat's wave function so fast and so completely that the cat is never in a genuine superposition. It's always definitely alive or definitely dead, long before you even think about opening the box. Decoherence is beautiful because it doesn't require any special mechanism. It just uses measurement interactions that already happen. But here's what bothers some physicists. Decoherence explains why the superposition becomes impossible to observe, but it doesn't explain why the wave function collapses into one particular outcome instead of another. Why did you measure the particle on the left instead of the right? Decoherence says the environment measured it, but that just pushes the question back. Why did the environment's measurement yield that result? So we still don't have a complete answer. Then there's objective collapse, a newer interpretation that says the wave function is a real physical object. It's not just a mathematical tool, and it spontaneously collapses on its own. When the wave function gets massive enough or complex enough, it has an intrinsic tendency to snap into one state. The larger the system, the faster the collapse. This explains why particles exist in superposition, but cats don't. It explains why the collapse is inevitable and doesn't require consciousness or special observers. The problem is we've never observed this spontaneous collapse directly. It might happen, but the time scale is so fast for small particles that we can't measure it. And for large objects, it's so efficient that we can't tell if it's happening or if decoherence is doing the work. And then there's many worlds which says, there's no collapse at all. The wave function never collapses. When you measure the particle, the universe splits. You observe one outcome. A version of you in a parallel universe observes a different outcome. Both are real. Both happen. There's no mystery about the collapse because the collapse never occurs. All possibilities are realized in different branches of reality. Think about that for a moment. Right now, in this exact second, you made a choice to watch this video. But in another branch of reality, another version of you made a different choice. Maybe they didn't click. Maybe they closed the window. Maybe they're watching something else entirely. But that version exists somewhere in some branch of the universe. Both realities are equally real. Both versions of you are equally conscious. Both experience different lives, different outcomes, different collapses into different realities. It's not mystical. It's just what the mathematics demand. Most physicists find many worlds philosophically troubling. It requires infinite parallel universes with every measurement, but it does solve the problem elegantly. There's no unexplained collapse. Everything is deterministic. Every possibility that the mathematics allows is realized somewhere. So here's the situation. We have at least 4 major interpretations, and they're all scientifically sound. They all make identical predictions for every experiment we can currently perform, but they're saying radically different things about what actually happens when you measure a quantum particle. How do we figure out which one is right? The truth is we're not sure we can. And not yet anyways. Some experiments have tested whether objective collapse is real. The results so far suggest it might be, but the evidence isn't conclusive. Decoherence has been confirmed extensively. Particles definitely interact with their environments in the ways decoherence predicts, but again, that doesn't prove Copenhagen is wrong or that many worlds isn't happening. This is where physics gets honest about its own limits. We have equations that work, we have interpretations that explain the data, but we don't know which interpretation is actually describing reality. We don't know if reality is fundamentally deterministic with infinite branching universes, or if it's fundamentally probabilistic with genuine collapse, or if the question itself is meaningless and we should stop asking it. What we do know is that something changes when we measure. That's not interpretation, that's fact. Before measurement, a quantum system has no definite property. After measurement, it does. That transition is real. We see it in every laboratory every day. Why does this matter? Why should you care which interpretation is right? Because this is the foundation of existence itself. The wave function describes reality at its most basic level. If we don't understand how the wave function collapse works, we don't understand how the universe creates definite facts from possibilities. We don't understand the boundary between the quantum world and the everyday world. We don't understand why time moves in one direction and not another. We don't understand consciousness or free will or what it means for something to be real. Every question about reality ultimately traces back to this mystery. And here's what's truly remarkable. Despite not knowing the answer, quantum mechanics works. It's the most successful theory in the history of science. Every prediction is accurate. Every application works, from semiconductors to lasers to the devices you're using right now. Quantum mechanics describes how atoms behave, and engineers use it to build technology that shouldn't exist if the theory is fundamentally flawed. So we have a theory that works perfectly while describing mechanisms we don't fully understand. Maybe that's telling us something too. Maybe the universe doesn't care if our interpretations match reality. Maybe the universe only cares that our predictions match experiments. Or maybe we're just not asking the right questions yet. The wave function collapse remains one of the deepest unsolved mysteries in physics, not because we don't have data. We have plenty of data. Not because the theory doesn't work. It works brilliantly. But because we still don't know what's fundamentally happening at the moment of measurement. What actually collapses? Why does it collapse into one outcome and not another? Is the collapse real or just an appearance of knowledge? But these questions don't have accepted answers. Not yet. And that's okay. That's how science works. We build knowledge incrementally. We find questions bigger than the answers we had, and we keep looking. The wave function collapse mystery has taken us to the edge of what we understand about reality. And standing at that edge, we have to ask, what if our entire understanding of existence is based on mechanisms we still don't grasp? We're living in a universe where the deepest layer of reality, the thing that decides what's possible and what's real, still hides from our understanding. Where the equations work perfectly, but the meaning remains elusive. Where science has learned to predict reality without fully understanding it. And maybe that's the real lesson. We don't need to know everything to make progress. We just need to be willing to live with the mystery a little longer. But here's what's really unsettling. Some physicists have proposed an extraordinary idea. Perhaps information, not particles, is the deepest layer of reality. If they're right, everything we think we know about the universe may need to be reimagined. Next time, we explore one of the boldest ideas in modern physics. Is reality made of information